Hello everyone, my name is Roopesh and the topic for my final project for deep learning is classification of musical instruments by sound. The idea is to identify the instrument that is being used to produce an audio clip or that is part of an audio clip. So I chose to run it on my local machine. It has got an i7 and 16 bits or 16 GB of RAM. For software, it is going to be an Anaconda Python package. So Anaconda platform with Python of 3.6, and then I have installed all the required packages like TensorFlow, Keras, Librosa, which is the sound processing library from Python for Python, and then Matplotlib for any visualizations of the audio or the results. And coming to the dataset, I found one music instrument dataset, IRMAS, that I have decided to use with the project. This consists of audio clips that are recorded with 11 different instruments like cello, flute, guitar, piano, saxophone, and violin, etc., and some human voices as well. And there are like a lot of files for each category of instrument. Like each instrument, there are variable number of audio files that are supplied. All these training files are like 3-second files. If you visit the website, they have the data set that is available readily for download. Yeah, so we can download it. It's pretty big data set of like 3 GB data set for training, and then 2.29 GB for testing. So if you get into training data, it is organized as instrument labels, folders that can be used as labels for identifying the instrument, and each of them has got a lot of files in it. Even the name has some kind of organization towards it. The first part of it is the instrument, and the second part is the genre of it, if we want to classify genre. So this is kind of interesting data set. And then coming to the test data set, it is organized a little differently. So it has got the wave file and an annotation file that is supplied with the same name as text file, and that has the instrument name. If you see, the training data is all 3-second files, but here we have varying number of varying size of files. Like the duration ranges between 3 to like 20 seconds. So each of them probably will have multiple instruments as well. So this is kind of interesting to see how it works. So I'm going to use this data set and probably train and evaluate my model with it. Coming to the steps of it, we'll have to download the data set and then extract the wave files into the folders in a working directory, which I chose here. This is my working directory, and then this is how it looks after downloading, just to give an overview. So there are some data pre-processing and preparations if you like. Because this is an audio file, we will have to convert into some kind of encoding vector that can be passed in. So one of the popular extraction feature is using MFCC feature, which is Mel frequency septal coefficients. This is one of the popular technique for encoding speech signals. This is how MFCC is arrived at. So we take a Fourier transform of the signal and then the log Mel scale, and then take the log to the powers of the Mel frequency, so we can find out like the highest frequencies and the lowest pitches in it, and then do a discrete cosine of the Mel log powers, and that resulting signal will be our MFCs. So MFCs. So coming to the pre-processing, I have few steps here that we are going to use as part of the features. This get labels, for instance, actually creates the labels from our folder structure for the training data, and then we have a handy function for wave to MFCC. We load all the wave files, and then we load them into Librosa package that converts into sample frequencies. We can have multiple parameters like duration, etc. We'll come there when we go to testing, because we have varied number of sizes. And then this is a sampling rate. We can pass it like 16,000 or like 44,000. 16,000 seems to be doing a better job. And then we have MFCC method that actually extracts the MFCC vectors out of it. And then a couple more to train and split. So using sklearn train split method, we are going to pass our training data, and then we get a validation split of 70-30, 70% for training, and then 30% for validation. And then there is another small function that saves all the arrays of each instrument type into an NumPy file, so that we can actually load it whenever we need it. So coming to the model, I have decided to use convnet model. So I have added a few con2D layers with high filter sizes, so it can be a little more effective with the audio files because of the vector sizes. In fact, because I have chosen my vectors MFCC feature size to be 64, so the size is a little higher. So I had to go with a little bigger filters, more number of filters, so the vector size is higher, and then the model is a little more effective with the higher sizes of it. So I have already also added some more max pooling and dropout layers as well. These should help with the model not doing overfitting very quickly, and also some kind of regularization during the learning process. Coming to the activation, final layer of activation, since it is a classification problem, we go with softmax, and then we supply the number of classification classes that we have in this case, which are those 11 elements, 11 instruments. And then loss is going to be categorical cross entropy, since we have to do a classification kind of problem. Coming to optimizer, ADA delta seems to be doing good job. I did try with some other optimizers like gradient descent, SGD, and Adam optimizer as well, but this seems to be a better option for audio vectors. I even tried with a learning rate of 0.001 for Adam and SGD, but that did not seem to help much. So this is a NumPy file that I have saved. All of them should be saved here as NumPy files for each of the instrument. And then this is a sample audio file, if you will. This IPD is a Python display library that is handy to make audio files play within the Jupyter notebook itself. And then this is the model that I have described. So looking at the summary, probably I ended up with about 500,000 parameters, which I think is pretty a big deep neural network. And then for executing the model, model.fit, I did like 50 epochs with a batch size of 100. It was taking a little longer, if you see, but then I ended up with an accuracy of about 55%. I tried in Google Colab as well. The accuracy seems to be around 55 with this convnet models. And to visualize the loss and accuracy of the training and validation files, I wrote a small helper method that will do the plotting for both loss and accuracy based on the history object that we get out of the model. And this is the visualization for the loss and accuracy for my model. Both of them seems to be the accuracy seems to be at around 55% for my model. And coming to the test data, since we have an interesting test data, so we have a company file that has this test data, and then we have to read the wave file as well. So to test it, I just if you see, it is longer than 20 seconds in some cases, and if you plot it, this is how the wave file looks. So for Librosa, we have an optional parameter that we can pass for duration. So we can pass the duration of it, and then it should trim it to whatever duration we mentioned. In this case, I stick to 3 seconds just to show the plot, and the plot looks good. And then now to predict it, we can actually pass it through the model.predict just to show the predicted instrument is electric guitar, which I think matches with the wave file that we just played, and then the actual instrument label that is from the text file that is accompanying it. So the model seems to be doing good job at recognizing these. And then for creating the test data, so I had to write a small helper kind of thing to actually prepare the data. This is kind of data pre-processing that we did for training, but in this case it is the text file that I have to get in. So I read it from the test file, and then I create the labels, and then I append both of them, the array and the label, so that I can convert it into a NumPy array and then feed it to the network. So this is kind of the pre-processing that we have done with the test data. So I have about 800 files with the same size vector, and then the 11 hot encodings. So if we run the model.evaluation, it comes to about 30%. So I have seen it for 30% of it. On the side note, if we visualize the audio files, so this is how the spectrogram looks, and these are the features that we can see from the sound wave file, the Fourier transform, and then the MEL spectrogram. So coming to the conclusion, I think the test data is a little more challenging in my case, because the size of the audio is longer, and it is not the same as the training data. And then the other interesting part of it is there are multiple instruments in the audio file. Probably that is making the model more difficult to evaluate or predict. So CNN model does work well with the non-image files as well, and MFCC will be the go-to technique. There are some other use cases like genre classifications, or tagging same audio instruments together, or music recommendation engines that we can actually apply on these. So what next? So probably I should try with RNN or GRU networks, and pass it through and see how it compares against my convnet model. And then there are a few data augmentation techniques that I came across, like pitch shifting, background noise, that can actually help with learning process. And maybe I should give it a try. Data sets, and these are the data set acknowledgements that I have to give it for IRMAS, and this is really good data set. And thank you for listening in. Thanks, Zoran, for this opportunity.